Hi everyone, my name is Yanqi. Today I will talk about some progresses that we've made on compact heterodyne interferometer design. This heterodyne interferometer that we developed can be considered as an option for ground testing and an alternative way for measuring free-falling test mass. Here it shows a typical heterodyne interferometer configuration. We use two laser beams with different frequencies. These two laser beams can be generated either from different laser or they can be from the same laser but passing through a frequency shifter. So one beam is hitting on the reference mirror and the other is hitting on the target, which could be the free-falling test mass in our case. The test mass is supposed to move in the same direction as the laser beam. So after reflected by the mirror, the laser beams pass through the quarter wave plate, changing their polarization states and reflected by the beam splitter. After that, the two beams are recombined together and interfere on the photodetector. So here we can also use a quadrant photodetector to perform the differential wavefront sensing. So in the ideal case, which means that there's no noise in the system, only one of this setup is enough to measure the target move. Of course, here we assume that the frequency difference between two beams are static and is already known. Then the target displacement will be indicated by this signal phase term. But in the real world, there's always going to be noises in the measurement system. It can be the laser frequency fluctuations or it can just be environmental or random noises. So in this case, we would want a separate interferometer to help us measure these noises and subtract them from the real measurement. Here the phi R represents the reference interferometer and the phi M represents the actual measurement interferometer. So a more precise measurement for the target movement can be acquired only when the noises are monitored and subtracted. So based on this concept, here's our design for the compact heterodyne interferometer. So let me walk you through this design. First, we use two identical equilateral triangular prisms. For each of the prisms, there's a splitting surface in between. It's a 50-50 splitting for a given incident angle. And we have the side surface to be reflective. In the middle, we have this polarizing beam splitter, and finally we have the quarter wave plate integrated on the interferometer. So we have two laser beams with frequency f1 and f2 incident perpendicularly onto the triangular prism side surface. When the ray hits the splitting surface, half of the beam will transmit and the other half will be reflected, but both beams will incident onto the PBS perpendicularly. So in this case, the two laser beams will be split into four on the other side of the interferometer. The top two beams are hitting the reference mirror 1, which is fixed in the system. One of the bottom beam will hit the reference mirror 2, and the other will hit the moving target. So the top two beams are constructing this reference interferometer, which is used to measure the noises in the system, and the bottom two are the measurement interferometer. Both interferometers have the same path inside the optical element, except for this part because of the target move. This means that the reference interferometer will measure the noises pretty well, and the noises will match the noise in the measurement interferometer. After beams are reflected by the mirrors, they enter the interferometer again, reflected by the PBS, and finally go into the second triangular prism. So what happened in the second prism is the same as in the first prism, except for in the first prism the beams are splitting, but in the second one they're recombined together. So the top two beams go into this reference detector and the bottom two go into the measurement detector. By subtracting the noises, the test mass movement can be acquired. It also worth mentioning that for each of the interferometer, the optical path length is the same for two arms. This means that the configuration will be less sensitive to thermal expansion or contraction, which we usually refer to as dead path effect. The interferometer is designed to have a very compact form factor. The width of the center beam splitter is 10 mm, and the overall length is about 20 mm. So we have performed tolerance analysis on the design to determine the fabrication requirements. So we're expecting to have this component fabricated September to November this year. Also, we have designed this mount for the fiber collimator. It has 5-degree freedom by using this 3-piece flexure structure. And we have built and tested a benchtop prototype system to demonstrate the design idea. In this prototype system, the design is exactly the same, except here we are using the spatially separated optics instead of the triangular prism. For the source, we are using commercial frequency stabilized Heine laser with frequency shifters. So one beam has this 85 MHz shift and the other has this 80 MHz. So we can detect a 5 MHz beating note frequency on detector. For detectors, we're using commercial phase meter from Mucolab. The entire system is operated in air. Here's a picture showing the benchtop system that we built, and based on this system, we performed a few different experiments. The first experiment is this long-term stability test. In this test, only one mirror is used instead of 3 separate mirrors, and everything is static in the system. So we measure the displacement drift and calculate this linear spectral density plot from there. The displacement drift is about 0.3 nanometer over 2-hour measurement, and from this figure we can see that at 100 MHz frequency, the noise level is about picometer level. And the main reason for the residual displacement drift is that the temperature fluctuation is coupled into the system. To verify this, we measure the temperature and the displacement change at the same time, and we can see that the trend for the displacement is very similar as the temperature change. So we calculate the temperature and displacement variation range, and the coupling factor is about 5.4 nanometer per Kelvin. So this is about half of the number compared to the commercial interferometer. Also, we calculated the outline deviation of the original displacement, which is shown in this blue line here. The orange line shows the post-processed data after subtracting the temperature fluctuation contribution from the measurement. So this also verifies that the thermal coupling is a main driven factor here. By replacing the single mirror with the individual mirrors, we also measured the displacement using this benchtop system. The first test is the frequency response. So we measured the target on the piezo stage oscillating at 1 and 5 Hz individually. So from this measurement result, we can clearly see that there's 1 Hz and there's a 5 Hz peak standing out of the noise floor. Then we run a comparison between our interferometer and the commercial interferometer. So we measure the stage linear movement of 50 nanometer step over the 7 micron range. By subtracting the stage linear movement, here is the residual errors for both interferometers. And by having the Fourier transform, we can say that for the commercial DMI, which is in this blue line, there is a peak at 1 period, which means the periodic error for the commercial DMI is about 0.6 nanometer. But for our interferometer, which is in this orange line, there is no detectable periodic errors. Alright, for conclusion, we have designed this compact heterodyne laser interferometer that can be easily integrated with the ground testing equipment and also can be an option for free-falling test mesh readout. We are expecting to have this component fabricated September to November this year. And before that, we have developed this prototype system with the same design idea. And it eliminates the periodic errors and also achieved picometer level displacement sensitivity, which is operated in air. And currently, the system is operated with vacuum chamber and temperature sensor to have a better control of the environmental effects. Finally, we would like to acknowledge the financial support from NSF. Alright, this is what I prepared for this presentation. If you have any questions or comments, please leave them under this video. Thank you very much.